FluxCarotenuto of the University of Innsbruck in Austria and of CNR in Florence, Italy, is here in a pasture near Avignon, France, measuring the flux of bacteria into the atmosphere. So, Federico, can I ask you some questions about your setup, please?
Yeah.
Okay, so can you describe your material here, your equipment, please?
Yeah. The equipment I have here is something that I use to estimate flux of microorganisms from the surface to the atmosphere. The system is composed of different components. The first one are the microbial samplers, which are the two gray items you see on bottom and top.
That's a Burkhardt sampler, right?
Yes, exactly. This is a high volumetric sampler that samples air at 15 liters per minute and gives me a count of colonies on a petri dish that it's installed within the sampler.
Okay.
To correlate these concentration measurements to the flux of microorganisms, I also need a system that gives me the movement of the air masses, which means basically wind speed and temperature. For this part I have two systems which work which give me the similar things about this information. One is a slow system, a simpler one, which has two kappa anemometers at two different levels.
Okay.
And at the same level I have thermocouples to give me temperature. And the other system is at the top. And that tripod-shaped instrumentation is a sonic anemometer, which is able to give me information about wind speed and direction in 3 dimensions and very, very quickly at 20 Hertz, so 20 times per second.
Okay.
This allows to estimate also the turbulent quantity, so the turbulent part of the transport, which is the one which interests us. For the to be able to measure directly the flux using this turbulent part of the transport, you would also need to be able to measure the concentration at the same speed, so 20 times per second at least. Since we do not have this information for microbes, we don't have samplers that works that fast, I will use a mathematical relationship that puts together concentration and slow measurement to estimate the turbulent measurement and therefore give me the flux of microorganisms. For trace gases such as CO2 instead, we have this kind of instrumentation and we can measure directly this flux. The white instrument at the top is a Likers 7500 gas analyzer. It's an infrared gas analyzer which is able to measure, among various things, CO2 at, again, 20 cycles per second. So with the combination of those two instruments at the top, I'm able to give a direct estimation of the CO2 flux. For the CO2 flux exists the same mathematical relationship that I can employ for microorganisms. In fact, it was born for measuring this scalar quantity. And to see if my mathematical approach is sound, I will combine the information from the direct measurements of the flux and the gradient of CO2 I'm measuring in in a way which is similar to the microbial one. So inside that gray box there is a slower gas analyzer which works in a different manner, and it's a Likers 7000 differential gas analyzer which is able to measure CO2 at 2 different levels. By combining all of this information, I should be able to tell if my mathematical formulation for extrapolating the turbulent flux of CO2 works well with the direct measurement of a turbulent flux of CO2.
Okay, so overall, in summary, what do you hope to achieve then with this setup?
What I hope to achieve is, first of all, a simplification. Since there is no method to directly measure microbial fluxes, the first thing I hope to achieve is to validate the mathematical formulation that is used to evaluate microbial flux from this gradient method, this slow method. Second of all, if this formulation is sound, then we can simplify our measurement of microbial flux, because we can simply use simple kappa anemometers and thermocouples and some kind of concentration measurement, instead of having to work through sonic anemometers and more costly and complicated instrumentation.
Okay, well, thank you very much and good luck with the continuation of your work.
Thanks.